If velocity distribution in a laminar boundary layer over a flat plate is assumed to be given by second-order polynomial, determine its form using the necessary boundary conditions. In this question, you need to derive your own velocity profile, but that velocity profile need to be second-order polynomial. So how to solve this problem? First, you need to understand how to create your boundary condition. So what is boundary condition? So please see this image. So assume that this is our thin flat plate, and then we have a free stream velocity flow from left to your right. So it will create boundary layer, and we could imagine it, the boundary layer is like this. So inside the boundary layer here, we have a velocity profile, and for the boundary between the plate and the velocity distribution here, so we point as this point, and then the boundary between the velocity profile, which is 99% compared to the free stream velocity here, we could mark it as this point. So this is our boundary condition. So as it name, it is the condition in the boundary between the flat plate here and the velocity profile, and the boundary of the velocity profile and the free stream velocity. Then you need to know how to write basic equation for second order polynomial. So this is the general term for second order polynomial. You could write as u equal a plus by plus cy squared. So the idea is the maximum power for this equation must be 2. That's why it's called second order polynomial. So then, in this equation, we could see that there are 3 unknown parameters, which is A, B, and C. So we need to create 3 different equations, and then we need to solve it simultaneously to get what is the value of A, B, and C. So how to get that equation, that 3 equation? So we derive it from boundary condition as we see here. So for boundary condition number 1, so please refer to this one here. So we could say that at this point, at y equal to 0, the velocity, the local velocity u must equal to 0. So why it must equal to 0? Because it has no slip condition. So we substitute the value of y equal to 0 and u equal to 0 in this equation. We could say that the value of a must be 0. Then we could write that velocity profile becomes u equal by plus cy squared. Here, for condition at point number 2, so we could say that y is equal to delta and small u, local velocity, is equal to capital U. Capital U is the free stream velocity. Point number 2 can be referred at this point. So at this point, we found that at y-axis, the value here is equal to delta because this is the boundary layer thickness, and the velocity here, we assume that the local velocity is now equal to the free stream velocity. That's why we write small u at this point is equal to capital U, which is small u is actually the local velocity in this velocity profile, and capital U is the free stream velocity here. We substitute the value of y equal delta and small u equal capital U in the velocity profile of this. We could write, and it become this one. So we state this equation as equation number 2. At this point, it is okay for us not to write the value of C because the value of A, because the value of A here is equal to 0. Then for the third equation, we could optimize the meaning or the value at point number 3. Point number 3 is actually share with the point number 2 here. At point number 3, we could say that at y equal to delta, the du dy will equal to 0. So it means that from that point, there are no velocity changes according to the height of y. So the gradient du dy will become 0. So how to get the du dy? Du dy can be get by the velocity profile of u equal by plus cy squared. So we have this equation, and then we could write du dy of this equation is equal to b plus 2cy. Then we substitute the value of y equal to delta in this equation. We could get that b is equal to minus 2c delta. So we mention this equation as equation number 3. So now we have equation 2 and equation 3. We could solve it simultaneously. So as you could see here, we could find that capital U is equal to C delta square and small c is equal to minus U over delta square. So at the same time, we could find that B is equal to 2U over delta. Then we could solve our polynomial equation. So the basic equation is u equal by plus cy squared. We know the value of b and the value of c. So we substitute in this equation. Finally, we could simplify it as u over u equal to y over delta minus y over delta square. So this velocity profile is the same with the velocity profile that we discussed in tutorial question number 1. It means that the velocity profile for second order polynomial is actually constant of this equation. Please subscribe this channel, C23 Classroom channel. Thank you for watching.